Hello, this is Dr. Armand again. We'll be discussing the third part, I believe it's the second part of Lewis structures, molecular geometry, hybridization. So today's lecture we'll be discussing molecular or geometry, electronic geometry, molecular geometry, and also polarity. So that's what we'll be discussing during today's lesson. So sit back, relax, and enjoy the chemistry show. So I have a little cartoon for you today. Here are my two minions. And so one minion says to the other, "What do you do with a sick chemist?" And the other minion thinks, give them a popsicle. Where's Bob? If you can't heal them and you can't cure them, then you might as well bury them. That was just a lot in the mood as well. So let's get started with today. We'll be talking about geometry. So there are two types of geometries when involving Lewis structures. We have the electronic geometry, which is just based on the total number of electron pairs around the central atom. So again, for geometries, we're only interested in the central atom. And with electronic geometry, we're only interested in the total number of pairs. So we're not interested in whether it's lone pairs or bonding pairs. We're just interested in that they are pairs of electrons around the central atom. Now, one thing you have to remember is that we count double bonds and triple bonds as one pair. So you don't count, for example, a double bond. It just counts as one pair of electrons, not two. So we only count everything as one. And so there are 6 types of electronic geometry. And again, electronic geometry is just based on the total number of electron pairs. So we have linear geometry. Linear is very easy. You just have 2 electron pairs around the central atom. So this is electron pair 1, this is electron pair 2. Now with linear geometry, they're all going to be bonding pairs with 2 pairs of electrons. Next we have trigonal planar. And again, this is just the total number of electron pairs is 3 electron pairs. And the reason it's called trigonal planar because as you can see from the shape, it looks like a triangle. And so all the bond angles in a trigonal planar, when you have all bonding electrons, is 120. And we'll talk about more about bond angles in just a moment. So trigonal planar, we have 3 electron pairs. Now this can be a combination of bonding and lone pairs in this. Next we move to tetrahedral. Tetrahedral forms a tetrahedron, so that's why it's called tetrahedral. And you have 4 electron pairs. Again, these can be bonding or lone pairs of electrons. Bonding pairs are bonds. Lone pairs are only on one atom. And then we have trigonal bipyramidal, which is 5 electron pairs. It's kind of a cross between trigonal planar and linear. And then finally we have octahedral, which is 8 electron pairs. It forms a octahedron. And so, excuse me, 6 electron pairs because it forms 8 sides. So if you count the number of sides, it's a total of 8. So the maximum number of pairs of electrons you can have around a central atom is 6 because 6 means it's going to have octahedral electronic geometry. So you need to know these electronic geometries in order to assign them correctly. Now when you're reading a question, make sure that you read it carefully. Does it specify electronic geometry or does it say molecular geometry? Because those can be a little bit different depending on the structure. And we'll talk about molecular geometry in a little bit. So types of electronic geometry, I'll put some examples up here. Now, the key thing for electronic geometry is that you draw the Lewis structure correctly. Because if you don't draw the Lewis structure correctly, then you won't get the right number of pairs of electrons around the central atom, and then you may get the wrong geometry. So here we have BF3. We've drawn the Lewis structure. Remember, boron, in this case, has a fission octet, and it has 3 pairs of electrons around the boron atom. 1, 2, 3. These are 3 bonding pairs. So since it's 3 bonding pairs, it's trigonal planar electron geometry. Next we go to water, H2O. H2O, if we look around the oxygen atom, we have 4 bonding pairs of electrons. So 4 bonding pairs of electrons means it's going to have tetrahedral. Or excuse me, 4 electron pairs. They're not bonding, not all bonding. There's 2 lone pairs and 2 bonding pairs, but there's a total of 4 electron pairs around the central atom. So this would be classified as tetrahedral geometry. Next we have xenon tetrafluoride. Xenon tetrafluoride has 6 electron pairs around the central atom. This consists of 2 lone pairs and 4 bonding pairs. But we're not interested in the difference. We're just interested in the total. And so this would have 6 electron pairs. This would be classified as octahedral geometry. So again, if you can draw the Lewis structure correctly, you just count the number of pairs of electrons around the central atom. Keeping in mind that double and triple bonds are counted as 1. Now, so let me give you an example I forgot to put up before we get to molecular geometry. Let me give you some examples of a trigonal bipyramidal. So here, for example, if we have the molecule SF4, sulfur tetrafluoride. So again, you draw the sulfur, you connect it to the fluorines, now we have the lone pairs. That lone pair doesn't look good. Apologize, my lone pairs are a little bit sloppy today. But this is the Lewis structure of SF4. So now if we count the pairs of electrons around the central atom, we have 1, 2, 3, 4, and 5. So we have 5 electron pairs. So this would be trigonal bipyramidal electron geometry. Yeah, trigonal bipyramidal electron geometry. And then just to look at one other one, we'll look at the compound BeF2. So we draw the beryllium, we connect it to the 2 fluorines, then we put in our lone pairs. I'll try to do this one a little bit better. So this is the Lewis structure of beryllium difluoride. Again, it's a deficient octet, so we count the number of pairs of electrons around beryllium 1, 2. So this would tell us the beryllium difluoride is linear, has 2 electron pairs. So it's linear electron geometry. And so that's how we determine electron geometry, just by counting the total number of pairs of electrons around the central atom. Okay. Now with molecular geometry, this shows us how the actual molecule looks, so how the bonds are oriented. So here's where bond angles become important. And so with molecular geometry, we're distinguishing between lone pairs of electrons on the central atom and shared pairs. Now remember, double and triple bonds get counted as one shared pair. So remember that, that's very important. So double and triple bonds get counted as one shared pair of electrons. So first off, we have linear. So linear molecular geometry is the same as linear electronic geometry. And the bond angle, of course, is 180 degrees. And so this is what VSEPR theory means. It means valence shell electron pair repulsion theory. So that tells us that electron pairs like to be as far away from one another as possible. So again, VSEPR stands for valence shell electron pair repulsion theory, which states that electron pairs like to be as far away from one another as possible. And so for linear geometry, the obvious bond angle would be 180. And for linear geometry, it's the same for molecular and electronic, because you can only have 2 bonding pairs of electrons. Now with trigonal, with 3 electron pairs, so this was 2 electron pairs. With 3 electron pairs, you can have all bonding pairs or 2 bonding and 1 lone pair. These are the different combinations with 3 electron pairs. So you just see what we're doing is we're replacing bonding pairs with lone pairs of electrons. So for trigonal planar, the bond angle between all of the bonds is 120 degrees. But when we replace one of those bonding pairs with a lone pair, you see now the bond angle is less than 120 degrees. So for example, and we'll see this in a little bit, but BF3 is trigonal planar. So its bond angles are 120 degrees. But now if we look at what's called bent with 3 electron pairs, such as SO2, which has 2 bonding pairs and 1 lone pairs, now that bond between the oxygen, sulfur, oxygen is going to be less than 120. Now with 4 electron pairs, they can be all bonding pairs, 3 bonding and 1 lone pair, or 2 bonding and 2 lone pair. So all again we're doing is we're replacing bonding pairs of electrons with lone pairs of electrons. And so in the first example, you see that the bond angle for one that has all bonding pairs of electrons, tetrahedral, is 109.3. Now, when we remove one of those bonding pairs and replace it with a lone pair, now the bond angle is a little bit less than 109. But when we go to removing two bonding pairs, these two bonding pairs push these two bonds closer together, so it becomes a lot less than 109. So this lone pair is pushing these bonds closer together. And that's the same that happens with the 3 electron pairs too. This lone pair of electrons push the bonds closer together so that their bond angle becomes less than 120. Likewise, with 4 electron pairs, the lone pairs, whether you have 1 or 2, push the bonds closer together so that your bond angle is less than 109. And we'll look at some examples of these in just a moment. So again, the key thing here is to draw the correct Lewis structure, identify the number of bonding and lone pairs of electrons on the molecular ion, then you can identify the correct geometry. Now with 5 electron pairs, this becomes quite tedious, but we'll just say we start with all 5 bonding pairs, and then we start replacing bonding pairs with lone pairs. So with 5 electron pairs, bonding pairs, you see that the ones in the equatorial region are 120, and the ones on the axial, so this is axial, it's like on an axis, axial, they're at 90 degrees. But the ones in the equatorial, I have to use the text box for this. Equatorial, they're at 120 degrees. So what we're doing is we're replacing lone pairs of electrons in the equatorial region, and that causes a decrease in the bond angles. But notice when we get the linear, which has 3 lone pairs around the central atom and 2 bonds, we have 180 degrees. So regardless, linear is always 180 degrees. Now with 6 electron pairs, again, we start with all bonding pairs of electrons. We start replacing lone pairs of electrons. Notice here that we start replacing in the axial position for square pyramidal and for square planar. We start removing bonding pairs from the axial positions. But with T-shape and linear, we remove from the equatorial regions the bonding pairs. And so again, anything that's linear is always going to be 180 degrees. Now the 3 most common types of octahedral geometries that you most commonly encounter is octahedral, square pyramidal, square planar, and then T-shape and linear are less common, but they do occur. So again, the key to this is drawing the correct Lewis structure, identifying the number of lone pairs and bonding pairs of electrons in the molecule. So for water, H2O, we looked at it earlier. Here you'll notice it has 2 lone pairs and 2 bonding pairs. So its a molecular geometry is bent. Next we have CO2. CO2 has 2 bonding pairs. They're both shared pairs, so the molecular geometry is linear. For ammonia, NH3, we have 3 bonding pairs and 1 lone pair, so this is trigonal pyramidal. So these are the molecular geometries based on the number of lone pairs and bonding pairs on the central atom. Look at a few more. Here we have xenon difluoride. Xenon difluoride has 3 bonding pairs circled in green and 2, or excuse me, 3 lone pairs circled in green, and 2 bonding pairs circled in red. So since we have 2 shared and 3 lone pairs, this is linear molecular geometry. Next we go to chlorine pentafluoride. We have 5 bonding pairs and 1 lone pair. So this would be square pyramidal geometry. SF4, which we talked about earlier, has 4 bonding pairs and 1 lone pair. So this is what we call seesaw geometry because the bonds form what looks like a seesaw. So again, the key thing is to draw the correct Lewis structure so that you get the correct number of bonding and lone pairs. So here we want to identify the electronic and molecular geometry of IF3. This is the Lewis structure of IF3. So for electronic geometry, it has 1, 2, 3, 4, 5 electron pairs. So the electronic geometry is trigonal bipyramidal. Five electron pairs. Now for molecular geometry, we got to distinguish between lone pairs and bonding pairs. So for the lone pairs, we have 1, 2 lone pairs. For bonding pairs, we have 1, 2, 3. So we have 2 lone pairs and 3 bonding pairs. So for molecular geometry, two lone pairs and 3 bonding pairs. When you look this up, this is T-shaped. And that's because the bonds form a T shape, the bonding pairs. So it looks like a T. We get a better, do this in red, so you see it forms a T, and that's where the T shape comes from. We have BRF4 plus. What's its molecular geometry? So BRF4 plus, let me fix it up a little bit. Okay, so BRF4 plus, we have 1 lone pair on the central atom and 4 bonding pairs. So for molecular geometry, we have 1 lone pair and 4 bonding pairs. So you would see which one this matches with. This is seesaw, because the bonding pairs form a seesaw. So we see. That's where people sit, and this is the seesaw. So, So sometimes you may have multiple central atoms. We want to determine the molecular geometry for each central atom. So here in this one, carbon is a central atom and nitrogen is a central atom. So in organic compounds, you can have more than one central atom. And so we got to determine the geometry of each one. So first we're going to look at carbon separately. So carbon has 1, 2, 3, 4 bonding pairs. So carbon, 4 bonding pairs, which means it's tetrahedral geometry. Okay, now we're going to look at nitrogen. So nitrogen has 1 lone pair here, and nitrogen has 1, 2, 3 bonding pairs. So the nitrogen atom has 3 bonding and 1 lone pair. This is trigonal pyramidal. And by the way, group 2 elements can only have a max of 4 electron pairs around them. So they don't go beyond tetrahedral electronic geometry. So that's something to remember. With organic compounds, typically they're going to contain row 2 elements. These will not go beyond tetrahedral geometry. So that means row 2 elements can be linear, they can be trigonal planar, they can be bent, they can be tetrahedral, trigonal bipyramidal, or bent. Nothing beyond that. So here we have this carbon. We want to determine what the geometry of this carbon, the molecular geometry of this carbon is. So again, we look at this carbon. We have 1, 2, 3 bonding pairs. Remember, double bonds count as 1 pair of electrons. So since this has 3 bonding pairs, it is trigonal planar. So now we're going to we'll stop here. So that concludes today's lecture on molecular geometry and electronic geometry. Again, the big thing is to be able to draw the correct Lewis structure, identify the number of electron pairs around the central atom, and distinguish between which ones are lone pairs and bonding pairs of electrons. That way you can determine the molecular geometry as well. The next lecture will incorporate what's called electronegativity and polarity of bonds and molecules. So what molecules have a asymmetrical distribution of electron density, which are polar, versus those that have, symmetrical distribution of electron density, which is nonpolar. So on that note, we'll conclude this lecture, and until next time, Dr. Armand signing off.